So, for example, look at this guy over here. We have a wire with mass per unit length. Now, in physics, you have three kinds of densities because you could be dealing with problems in three different dimensions. Like, for example, 1D, 2D, and 3D. A 1D example is the one you're seeing right here, Amelia. It's an infinitely thin wire. So how you can think about these things is if you were a very small ant creature, how many directions of freedom do you have to move on your object? So you put in here right now a little line. If it's infinitely thin, you can only move along this direction. You can't move sideways at all. To me, that is one, again, coordinate of motion. This could be represented by X right now, and that's one degree of freedom, one dimension. But if you had something like a plane, let's say, right, then you could move this way and you could move that way, right? And these can be represented by X and Y. Add a Z on top of that, right? You can have, for example, a cube now. And this time you can move three different directions. You see that? And all of these are represented by a certain variable. So you need to be aware of the symbolism that we use for each of these densities, as we call them. You've probably studied in high school volume density, and it's like, you know, they told you to take the mass and divide it by the volume to get the volume density, right? That's the stuff that they've shown you in high school. So rho would be the mass divided by the volume, and the units would be kilograms per meter cubed. But there's other kinds of densities too. You can have a surface density of any property here. You can put any property you want here. That could be charge, mass, I don't know, money per unit volume, anything, right? And you can put it there. If you're dividing by volume, it's going to be a volume density of that property. So it could be anything. For our purposes, you're usually going to see mass and charge in the position of M over there. Okay, so what other densities do we have? If you have a surface, then the only difference is you're going to be taking that property and dividing it, as the name suggests, by the surface area this time. And that one will give you units here of kilograms if it was mass per meter squared. And last but not least, you can have a one-dimensional object, and you can have that property spread on top of that 1D object. And you, of course, would be dividing instead by its length now, for giving you here units of kilograms per meter if it was mass that goes on top of here. So what letters do we use to represent those densities? We use Greek letters again, but it's not rho. The surface one, we use sigma, this little guy over here. For the linear mass density or linear density, we use lambda. I guess sigma for surface, lambda for length. I don't know, kind of mnemonic there. But those are the densities that you're working with, and you know their units are going to be respectively whatever the property is over the dimension that you're working in.
Gotcha.
So now that you've got here a little line, a wire, we know it's 1D. So what letter would we use over here if it's one-dimensional? Which of the three?
It's gonna say the last one because it's one just meters.
Yeah. So it's a little wire, and so they're giving us, okay, given over here. Let me go on my chair 1 sec. There we go. So we're being given the mass per unit length. It says, and I might want to convert that because the units are terrible. 0.55 divided by 1,000, okay? That is 5.5 times 10 to the negative 1, 2, 3, 4 kilograms per meter. Okay. we carry a current. The SI unit for current is amps. So this is good, 2.14 amps. Horizontally to the south. Okay, I guess the wire here, I guess the wire needs to be oriented like this, and the current needs to be oriented like this if we put a north-south type of axis here. Fair enough. What are the direction and magnitude of the minimum magnetic field needed to lift this wire vertically upwards? Okay. So we want to find here the minimum magnetic field, B minimum, so that we lift, so that FB, I'm just telling you in mathematically, like how you would say that to yourself. We want the B minimum so that the force from this B matches what? What do we want to match?
Current.
So if you want to lift the wire off the ground, what should FB pointing up match?
The gravity force.
See, we have ourselves a setup, okay? And so you might be wondering, I haven't been given the length of the wire here. And I'm going to always say the same thing. When you ask these questions, I'd say, do you really need it? I guess here, if we were having a conversation, you'd say yes. How do I find the mass of the wire if I don't have the length of it, right? You've given me here mass density. I obviously need to multiply by a length here to get rid of this. And I'll say, are you sure about that? So, you know, this back and forth will end with me winning eventually, and I'll prove that you do not win by using the length. You want to use the length as a dummy variable. So I'll show you what I mean. You'll put it in there. Yes, this wire does have a certain length. I'm not going to say no to that. But why not work in a way where we're describing all of the other properties per unit length? For example, why don't we go and describe the magnetic force per unit length and then the gravity per unit length? You see what I'm saying? So if we do that, if we have this per unit length and this per unit length, the per unit lengths are going to cancel eventually when you set these equal. That's the idea, at least. So again, let's see. How do we lift this wire up, first of all? Well, enter the new right-hand rule here, okay, where we are supposed to, like, again, we're supposed to, I'm supposed to derive this for you. I feel like it's going to take a little bit. Maybe I should show you, just so you know. How do I get the force that would act on a wire that carries current I? Okay, how would I get that? All I know from last time, remember this guy? Yeah, that's all I know from last time right now. So how do I use this to derive the force on a wire now? Well, here's the thing. What is really V? Well, you would say it's related to the derivative of position, right? Okay, so I can write it like this right now. And then I can move derivatives around. So I'm still okay. This is still applicable to point charges, but let's say I wanted to apply that to a little infinitely small portion of a wire. Let's just look at this over here. There's a wire, and I have here a very small portion of it that contains charge dq in it. Very small charge, right, compared to the whole wire. And, you know, it also has a very small length. We'll call it here dx, okay? So I'm like, all right, what kind of magnetic field would this generate right now, right? This little dq, not the whole wire yet, just this little dq. What kind of magnetic field would it generate? And I want you to understand that this DQ is moving down the wire right now. We have a current. This is what the current indicates. It means that this guy is moving with some velocity down the wire right now. And these again are parallel. Like the current is telling you where the DQ package is moving down the wire, right?
Mm-hmm.
Okay. So again, these are going to be parallel. You go and look at your, again, Lorentz force equation and you go, hold on a second. If I want to find the force right now that this is going to feel due to a magnetic field that is, let's say over here out of the page. Let's put a magnetic field in the region. So there's our B. And we can do the right-hand rule here if you want to follow me. Look at how this DQ is moving. It's moving to the right. So put your thumb, because we have to do V crossed with B if you remember.
Mm-hmm.
We put our thumb again along V, and we put our index finger along B, which is like pointing toward our face. So the force should be pointing down for you when you do this.
Yeah.
Okay. So this force, of course, is going to be an infinitesimal. Why? Because we need to sum together to find the force on the entire wire. We need to sum together the forces that are going to be acting on all of these DQs, right?
Yep.
Because the wire is broken down into these little chunks. We need to sum them all together to get the FB. So for now, we're working with an infinitesimal here. Okay. And we've said that DFB right now will be the cross product between the charge and its velocity crossed with B. Now, you are never, ever, ever going to be given this. Ever. What do you think you're going to be given instead for a wire?
It's current resistance.
So we might want to change the formalism here to get rid of this guy. And you saw me start it over there earlier by sneaking in a derivative with respect to position, right?
Mm-hmm.
And I would do this instead. Now, a mathematician would be annoyed by this for reasons I don't want to get into, but you can move the differential from below over here, this guy, you can move the differential over here, below the DQ instead. What do you think the quantity on the left represents here? A change of charge over the course of time. What is this quantity defined as? How much charge? Yeah, the current. That's the current. That is the current. So you have I over here. All right, and then your equation becomes this. Now we're not done just yet, because you can see I have to find what FB is. Well, to do FB, truly you need to integrate, right, both sides. Skipping some details here, I'm going to show you what's going on. But in essence right now, this integral is not going to affect I because it's a constant. The I is going to get pulled outside. And then you're going to be integrating here along the length of your wire. However long your wire is, that's how long you're going to go for.
Mm-hmm.
So truly, I would keep this as the equation that finds the force for a current carrying wire. Because again, it really, the cross product matters, right? If these happen to be parallel, then you're not going to get a force on your wire. You know what I mean?
Mm-hmm.
So it's only when they make an angle that you get a force.
Yep.
How familiar are we with integration though?
Not at all.
Okay. Good to hear, so that we know how to proceed with this. All right, so I'm going to say here, if dx is perpendicular to b, okay, and we get a simplification for this, obviously. So this dumbs down now to this. You got the current, and then you got the integral of b dx. And then this is going from 0 to L. B, usually, again, you guys are never going to do a space-dependent B, believe me, okay? It's never going to be a function of x because you don't know integration. You just said it. So this B is going to be pulled outside the integral as well. And all you have left is literally just the length of your wire here. That's what's going on from 0 to L. And then you get IBO, which should be a result that you've seen before. Okay. So it is the current times the magnetic field times the length. We'll talk about the cross product though, because it's going to come into play. It does matter, the angle. I assume here it's perpendicular, so I show you like an example of what ends up happening, right? All right, so how do you solve this guy now? Now that we know, okay, we know how to use the new version. I would really like us to use this. I don't know. I really want you to use this because the information is all here. This is the general way of approaching this. And then we can dumb down the integral and throw it out. You don't have to ever integrate in 112, but you know, I just want you to understand. The only thing I want you to remember, if anything, this is equal to this, okay?
Okay.
Technically, you know, you have to go from 0 to x from that to be true, but that's it. If we use this, and you can replace this with L, you know, you can replace this with L. You can do whatever you want with this. You can call X, Y, you can call it Z. Nobody cares. As long as you remember the form, this here. Like, I think we can use this in conjunction with that, and it will be very good for you to keep the picture general instead of, you know, I think it's better to have the general picture rather than have a specific picture and try to work out a general picture from it. You're going to make mistakes that way, but the general picture, going to a specific scenario, you're never going to get it wrong.
Okay.
So with that being said, I'm going to use the right equation here to help us out. So what does it say here? It says we want to do this. Okay, I'm all down for that. So the magnetic field, let's see. A wire having a mass per unit length this much carries this much current. We need a magnetic field to lift it. So hold on for a sec. If this is the top view, then what's going to end up happening here? Where do I want the magnetic field to point? Where do I want the force to point? Think for a second. This is your wire, and you're looking at it from above. It's like you're having a perspective right now from above, and you want to look. Where should the force point?
Like into the page, like down.
I would move it, I would compress it against the ground.
So the opposite way.
The opposite, exactly. We want the force to come toward our face right now, correct? Right, because that will be FB right now. And where should gravity point respectively?
Down, like
into the page, exactly. Down or into the page. All right, so watch this now. You are doing the cross product between dx and b over here, okay? So you need to ask yourself, what kind of magnetic field am I going to need to produce this force right now? What kind of magnetic field? Let's do a right-hand rule. So we have I going down. That's our thumb. And our middle finger, I know it's going to be a little hard for you. Our middle finger wants to point toward our face right now. Our middle finger, not the index. So the middle finger right now once the point, you got to turn your hand, or you can do it this way. Again, whatever way you like better. So we want to, again, the middle finger, we want it to point toward our face. And look, naturally the index, sorry, opens for me to the right for that to happen. My middle finger, I don't know if you can see it, my middle finger is pointing toward my face as I require for the force. It's pointing toward my face. And then the index finger naturally opens up to the right. So we need a magnetic field that points to the right. We got that out of the way. So, okay, then what else can I do here? Let's see. Look at the magnetic field and let's take a look at a chunk of the wire right now, this DX guy. Hold on, let me again take DX right there. All right. So here we go. And look at the DX. Look at the magnetic field. What's the angle between them?
90 degrees.
DX is perpendicular to B. Let me just, one sec, let me just pause one sec right here. So what we have going on over here, we have the fact that these are perpendicular. So again, this dumbs down when we do this. I showed you previously that it dumbs down to I times B times the length of the wire, whatever this length is. But we were saying that I'm not a fan of having the length here on the right-hand side. I want to find the force per unit length right now. That's what I want to do over here. Force per unit length. It is going to be the product of I times B. There's your equation 1.
Mm-hmm.
So then you go and ask the same question for gravity right now. You go, what's the formula for gravity? Do you remember?
mg.
All right. But again, you don't have this m, rather you have lambda. And I want to remind you what lambda was. How do you think you can get m?
Lambda times length.
So exactly what I'm going to put in. But again, am I going to keep the L on the right-hand side?
No.
No. I'll find the force per unit length for gravity. You see that?
Mm-hmm.
Now, what do I want these two equations to be? I want to lift the wire off the ground. I want the magnetic force per unit length to be what compared to the gravitational per unit length?
Like going in the opposite direction.
And being?
Negative and positive.
Besides the direction, though, the magnitude should be?
Like positive and negative? No? Because one's going up, down.
Right, they're going in opposite directions. But again, if I am to barely lift this off the ground, what should the size be?
Greater than the one pulling down.
That would give an acceleration, right? If we have a residual net force, we'll get an acceleration. We just want to hover over the ground.
So they want to be equal.
So again, to lift wire, 1 is equal to 2. And there we go. You see again what happens here. We get the current times the magnetic field strength is lambda times G. And then I can get what the necessary magnetic field needs to be. It's that simple. Once you get it, once you get the understanding of it. All right. And of course I can get the numbers for that, I guess. 5.5 exponent negative 4 times 9.81 divided by the current, which was 2.14. I need here a very small magnetic field to do that. 2.52 times 10 to the negative 1, 2, 3. There you go.
Makes sense.
All right. So how do you feel about this? Is again a side on the right, just deriving the equation that we need. But how do you feel about the problem? Like we wanted to make gravity equal to the magnetic force. The goal, of course, was to find first, where does the magnetic field point? Well, you go, if this is dx, always aligned with I, by the way. These two are always parallel. In fact, this is the direction of I, right? This is the direction of I. So we found again that this, with this in combination, we'll need a magnetic field like this. We dumbed down the integral here because these are perpendicular. We got this. Then we divided both sides by L. Did the same for gravity. Used the linear mass density and then divided both sides by the length. Equated the forces per unit length and solved for B. And that's it.
Makes sense. It didn't at first, but it does now. So it's all
Exactly.
good.
So I got Hafsa coming in right now. I'll pause for a sec the recording. See if we need to record the rest of it.